exercise 10, we consider a homogeneous Poisson process on the non-negative real axis with arrival times, t1, t2, t3, and so on, and with inter-arrival times defined as the difference between two consecutive arrival times. So let's just add here that we assume the intensity, so that we assume that the Poisson process has intensity lambda, in the sense that Wi are each exponentially distributed with parameter lambda, because that's part of what it means to be inter-arrival time for a homogeneous Poisson process. That means that it is exponentially distributed with some parameter lambda, which is also the intensity of the homogeneous Poisson process. Now in A, we're asked to show that the arrival time t1 has the forgetfulness property. And what does that mean? Well, we're asked to show that given that we know the first arrival occurs after time t, this, we just need to show it for different t and s. Yes. So given that we know the first arrival time arrives after time t, what's the probability that it will not just arrive after time t, but it will arrive after time t plus s? So given that we know that at time t there has not been an arrival yet, what's the probability that there will not be an arrival in the next s time units? Well, that probability we want to show is just equal to considering the probability that there is no claim up until time s. So in that way, we can kind of say that t1 resets itself all the time. Yes, it always resets itself. So no matter how far along we are in time, it's as if it was just a newborn baby all along. So let's just try to show this. It's pretty simple, really. The probability that t1 is greater than t plus s, given t1 is greater than t. So this is just the probability of one event conditioned on another, which, as we recall, is the probability of the intersection of the events divided by what we condition on, probability. So this is the probability of t1 being greater than t plus s and t1 being greater than t, divided by the probability that t1 is greater than t. And up here, we can see in the numerator that if t1 is greater than t plus s, then definitely it will be greater than t. So this is, we have kind of a redundant statement up here, so it's enough to just write that t1 has to be greater than t plus s and divide by the probability that t1 is greater than t. Now recall that t1 is the same as w1, which is exponentially distributed with parameter lambda, which also means that the probability that t1 is greater than just any value x is given as e to the minus lambda x, because that is the survival function in the exponential distribution parameter lambda. So this is equal to e to the minus lambda t plus s divided by e to the minus lambda s. And so the terms with lambda s, they cancel out, and what we're left with, divided by e to the minus lambda t. Yes? So the terms with t, they just cancel out, and what we're left with is e to the minus lambda s, which is then again the probability that t1 is greater than s. So that was pretty simple.